All right, today we're looking at Euler's method, growth and decay, or exponential growth and decay, and logistic growth and decay. This will be a very fast video because we got a lot of topics we're getting through. So I'm not going to go through as much of the in-depth stuff. So Euler's method is a way of approximating a solution to a differential equation by using the idea of the equation of a line. So we're going to be saying our new y value, okay, is going to be equal to the rate of change, the dy over dx, times the change in x, plus our old y value. Okay? New y value is dy over dx, which is the rate of change, times the change in x, plus the old y value. So the three things we need the rate of change, the dy over dx, we need the change in x, and we need an initial point, a x naught comma y naught. So when we look at a problem like this, we have the dy over dx, we have an initial condition, our change in x, our delta x, is going to come from the number of steps. We want 4 steps to go from -1 to 1, starting at x equals -1, ending at x equals 1. So that means our change in x will have to be 1/2. So we're going to set up a chart. We have we'll start with initial. Euler's, give myself a little more space, and then new. So our initial point is -1, 2. Our Euler's method is going to be the rate of change at that point, which is 2, times the change in x, which is 1/2, plus the old y, which is 2 again. And then we're going to plug that in. We get our new point of something, 3. Well, that means we need our new x value. We said our change in x is 1/2, so our new x is going to be 1/2 away from this x value. So -1 plus 1/2 is -1/2. And we do it again. Now we have this new point. And we're going to keep doing this process until we get to the x value we want. So we have our slope, which is 3, times our change in x, plus our initial, which is 3 again. So 3/2 plus 3 is going to be 9/2. And then our new x is 0 this time. Now we have 0, 9/2. This is going to start getting real ugly real fast. So we have 9/4 plus 9/2. We get 27/4. And our new x is 1/2. So we have 27/4 times 1/2 plus 27/4. And we have our new y of, oh gosh, so we have, that's going to be 56 plus 20, no. Yeah, 54. 54 plus 27 is 81/8, and then our new y, or new x is 1. So now, once we've gotten to the right x value, we stop and we say, okay, y of 1 is going to approximately be 81/8. And that's Euler's method. All right, next we're going to look at exponential growth and decay. We're going to just start with exponential growth and decay, and we'll look at logistic growth and decay in a minute. So exponential growth and decay comes from this formula right here, where a naught is your initial, k is your proportionality constant, t is the amount of time, and y is your final. We're going to be having different problems that all apply to this. You'll have ones like prime rates or growth rates or half-life. We're going to do one that's like this, and I'll let you see how it works out. So 5-year period, crime has dropped by 40%. There were 1,200 crimes at the start, so that's telling us 1,200 is our initial. When will the number of crimes drop below 300? So we're looking for when is this going to be 300. The issue is we don't know k, and that's where this first bit of information is going to come from. We do know that, that after a 5-year period, it was cut by 40%. So that means 60% of the crime is left. E to the k times 5. All right, so after the 5-year period, it's cut by 60% or 40%. So 60% of this is going to be 7. Ooh, I have to do this in my head. $720. Okay, and then we can solve for k by just rearranging. So we have 72 over 120 equals e to the k times 5. Natural log of 72 over 120 equals k times 5. K is equal to natural log of 72 over 120 all over 5. Plug into the calculator. Now, when we plug this into the calculator, we want to make sure that we are storing our decimal so we can get as accurate a value as possible. Oops. And so we get k is approximately negative 0.102, but this is not the exact, this is our approximate. We want to store this value, and then we can use it in this equation right here. So we have 3, well, really, we're going to divide fully, so we're going to have 1 over 4 e to the k, or equals e to the kt. But we know what k is because we just stored it. So we have natural log of 1 over 4 divided by k equals t. We can plug that into our calculator. And we get t is equal to 13.569. So about in the year 2003 is when crime will drop below. So you see a bunch of different problems that use this and use this idea, so I'll let you try those. Last is logistic growth. Now, logistic growth is a model in which it grows really fast and then flattens out at the end. These are two formulas that both model logistic growth. Both are completely accurate and completely okay to use. K in this case is our constant of proportionality. Y is the amount, and M is our max. M is our max. These problems really try to do a lot to trick you and to make you think they're not as easy as they are. So you'll see something like this. Find the limit of the function p of t as t approaches infinity if p prime is equal to this. Well, if we rewrite this slightly, and instead of saying p prime, say dp over dt equals 7.2p 3200 minus p. Well, this is just a logistic growth problem where p is our y, 7.2 is our k, and that would leave 3200 because p is by itself. If we look, that looks exactly like this equation right here. Since p is by itself, that means 3200 must be our max. And so if that's our max, the limit as t goes to infinity of p of t is going to equal whatever the max is. So that's just going to equal 3200. It's not going to get much more complicated than that. The most it'll do is actually make you create the equation yourself. But in a problem like this, if you read through it, you'll see that this 2000 is the max, this 400 is your p, and this 500 is the dp over dt. You're going to use those three things to solve for k, and then you're going to plug them back in to create your equation. You'll never be able to solve this differential equation in this class. You won't be able to do it until you're in DiffyQ in college. So it's not like you're trying to solve the logistic growth differential equation. It just says to write the differential equation that models it. All right? So that's everything for today. Let me know if you have any questions. Y'all have a great day.